Hello, we're going to be starting chapter 3 today, which is all about representing data. Lots of the ideas here you'll find are familiar from GCSE, a couple are expanded on, a couple are done slightly differently at A level. So this is mostly summary, but with a few bits and pieces that are quite important to learn. In year 1 we met the idea of outliers. Outliers are anything which are significantly different to the rest of the population, where we can try to work out if they are errors or if they're just particularly large bits of data or particularly small bits of data. So at A level we're always given a rule for calculating these things. So sometimes it uses standard deviation, sometimes it uses quartiles. So we're going to consider something an outlier if it's greater than the upper quartile plus some multiple of the interquartile range. Sometimes it's 1, 1.5, 2. So remember the interquartile range, Q3 take away Q1, give us an idea of spread. So if you're the upper quartile plus some amount of spread away from our data set, we're going to call this an outlier. Similarly for the lower quartile, we're going to use Q1, take away some multiple of interquartile range. Again, sometimes this uses standard deviation instead. Here we've got an example. They give us 30 bits of data, which are on blood glucose levels. They also give us a rule here, which is 1.5 times the interquartile range. So if we look back to this is K as 1.5. So we are an outlier. If you imagine your upper quartile and then you go along 1.5 interquartile ranges in the upper direction, if it's outside that, we're going to say we don't quite believe this bit of data. So finding our quartiles, we first need to decide what type of data this is. This is list data, so we're going to use the choosing method for list data. So to do Q1, the first thing we're going to do is work out where this is in our set of data. So we're going to do 30 because there are 30 things divided by 4, which gets us 7.5. Because this is a fraction, we're going to round up and we're going to do the 8th thing. So we're going to flick through this data set and find our 8th thing. So we've got 1, 2, 3, 4, 5, 6, 7, 8 is 3.2. And this is Q1. We're going to do exactly the same thing for Q3. This is 3 times 30 over 4, which gives us, let's grab a calculator, 3 times 30 divide 4, which comes out to be the 22.5. So we're going to use the 23rd thing. So counting through for the 23rd thing, so counting through for the things, we've got 15, 16, 17, 18, 19, 20, 21, 22, 23 things, which is a 4.0. So I'm going to write down my 4.0 in here. So now I've got them, we can work out interquartile range, which is actually 0.8. So when we come to look at our upper bound, this is Q3, which is 4.0, plus 1.5 times 0.8. This is 1.5 times the interquartile range. This comes out to be 5.2. Because this comes out to be 1.2 plus the 4, we get 5.2. Our lower bound for outliers, and it's really important to write these bounds in because this is where most of the marks are, is going to be our lower bound, which is, so our lower quartile, which is 3.2, take away 1.5 times 0.8, which comes out to be 2.0. This gives you 1.2, we take it, we get 2.0. So we've got our two bounds for outliers. Having a look at our data, is there anything bigger than 5.2? If we look at the top end, there actually isn't. Is there anything smaller than 2.0? If we look at our lower end down here, we've got 1.7. So this means 1.7 is an outlier. Okay. Moving on to this next example. This next example asks us to use mean and standard deviation. So the first thing we have to do is calculate our mean and standard deviation. So if you remember for our mean, we have the x bar is equal to sigma x over n, which is 252 over 12, because we get told there are 12 African land snails in here. So we get 252 divided 12, which is 21. It's always worth looking at our data. 21 looks sensible. There are a couple of bigger land snails in here, so that's going to move the mean up a little bit. Sigma x, we're going to use the formula square root sigma x squared over n, take away sigma x over n all squared. And we're going to put this in our calculator. So we've got a big square root, fraction, we've got 5468 over the n, which is 12. Take away 21 squared, because 21 we got here from doing our sigma x over n. If we press equals, we get a standard deviation of 3.83. Which is our standard deviation. So they've said that an outlier is anything that lies plus or minus 2 standard deviations from the mean. So our upper is going to be 21 plus 2 times 3.83, which is, so 21 plus 2 ants, 28.66. Our lower bound is our mean, take away 2 lots of 3.83. Because if we look here, it is plus or minus 2 standard deviations away from the mean. If we work this out, we have 21 minus 2 times 3.83. We get a lower bound of 13.34. So we've got our 2 outlier bounds here. Now we need to have a look at our data and see if anything is outside of these bounds. Hopefully you can pick out that 32 here is bigger than our upper bound. So 32 is an outlier, as 32 is bigger than 28.66. It's really important to write down your outlier bounds here, because these are where the method marks come in, and then identify that 32 is our outlier on the grounds that it's bigger than our upper bound. Okay, just a quick note on cleaning data. This is the process where we get rid of things that are clearly anomalies or errors, rather than things that are a big set of data. For instance, we look here in this example, they give us the idea that there's 165 here, and this is age of people at a birthday party. Now 165 comes out to be bigger than our outlier bound of 135. It's clearly an error rather than just a very large amount of data. If you look for Google and find out the oldest age of the person who's ever lived, it's probably going to be in excess of 130. Sorry, in excess of 100, but not as high as 135, and definitely not as high as 165. So maybe someone's put the 1 in by accident and it's 65. Maybe it was 16 or 15, and they've put an extra digit in here. So this one we could take out of our data set and then carry on with our calculations, like finding the mean and standard deviation. We're going to have a look at this exercise now, so pause this, have a go at a couple of these questions. Remember to let your teacher know if you want any help with any of the questions. As a quick reminder from GCSE, Boxplots are still the easiest way to draw out a set of data and compare one group to another, and they give a nice visual representation. For this, you need to know the lower values, the quartiles, upper and lower, and the median, and if there are any outliers. So a typical question might ask you to find the outliers before you do your box plot. The only thing that's interesting is the blue one that we have here. Sometimes we're given information like there was an outlier here at 165, and if we just go on the previous question, the next one was 62. So sometimes they give us the information and we can plot this up a bit here at 62 as the highest non-outlier. Sometimes they don't give you that information, and we have to plot the upper bound for this. So if you've got the value, plot it, but if not and you're wondering what to plot, we can't just miss it off, or we can plot our bounds for outliers here if you're not given a highest value that isn't an outlier. So I'll give you a second to add this to your notes, and then we're going to have a look at comparing. Okay, I've actually done part A by copying out the answers. So here we plotted our lower quartile, we plotted 3.6, lower value, highest value, all these things. So we plotted this from our information in the question. So the first thing we did was work out outliers. 1.4 turns out to be an outlier. Our lower bound is about 1.9 something, so we plotted that here because we're not given a lowest value. When we come to do our comparison for part C, there are three things we need to compare. We need to compare the median, and as we can see from here, the males, the median is higher than the females. It's blood glucose level, so it's not a competition. This one here is higher, so for the males the median is higher. The interquartile range for the males is also higher. This gap here between the lower and upper quartiles is bigger for the males than it is for females. The other thing we can talk about are outliers. There are both one outlier for each of these two sets of data. Some mark schemes let you compare the range, but occasionally, so the range would be from here to here and here to here, but occasionally mark schemes don't allow range. So I would stick to median, interquartile range and outliers. So this is usually have as a discussion exercise, what things could you compare for this? So for A, the mean is higher, so the median is higher than B. For A, the interquartile range is higher, and this one has one outlier, this one has no outliers. Those are your 3 points. I'd like to have a go at question 2 and question 3. You can do any of the rest of these questions if you want, but these should be enough to just jog your memory on Boxplots. For the final part of this, we're asked to look at cumulative frequency diagrams. You might have met these at GCSE. I've not seen an exam paper question that asks you to draw them, but quite often they give you a cumulative frequency diagram and ask you to get a conclusion out of it. So I've copied one from the textbook. So here is my cumulative frequency diagram. Just a couple of things to have a look at when plotting these, because some people plot these incorrectly. So we start off plotting down here. Let's use this to point with. So we start off plotting down here at the bottom at 4.60, because if we look at a table, there are no things below 4.6. The next point we plotted is actually at 4.84, so we're plotting the top of each of these classes. So at 4.8 we plot 4, 5.0 we plot 7, 5.2 we plot, this is frequency, not cumulative frequency. So actually at 5.0 we're plotting 11, and that does come this because it's the 4 and the 7, and then we plot 26 for the next one, and all the way up until we get to our 80 giraffes at our top interval at 5.8. So plotting this is really important. When we come to find the median, so for part B we're asked to estimate the median, we go through our cumulative frequency and we pick thing number 40. We scroll along, we rule down, we work out what this one is, being really careful with this scale along here. So if you're going to do this, accurate grid paper is really useful. If you think that your one isn't particularly accurate, feel free to use the one in the answers to do these calculations. Estimate the lower quartile and the 80th percentile. So for the lower quartile, we're just going to do 80 divided by 4, or times a quarter, it's the same thing, which gives us 20. So we're going to go through and we're going to pick out thing number 20. This uses a method a bit more like interpolation, so we're not going to add or multiply or take an average or anything like that, because this is continuous data that we have in here, it's height, and we've got grouped data in our table. When it comes to doing the 90th percentile, we're going to do 80, which is our thing, and then we're going to times it by 90 over 100. So this is 80, which is the number of things, times 90 out of 100 to get the 90th percentile. So if we do this on our calculator, we have 80 times 90 out of 100. We get 72. So when we come to calculate this, we're going to look at thing number 72 here, scroll along, rule it down, read off the bottom. It's just over 5.5. We could then use our quartiles to draw a box plot for this data because we've got the lowest value, which is down here, the highest value, which is up here, and we've got our quartiles. So we've got our lower quartile, we need to work out our upper quartile, which would be from 60, and then we've got everything we need to draw a box plot. Now we need to have a go at exercise 3C. Again, if you don't have accurate graph paper, you might want to use the box plots, so the cumulative frequency graphs in your answers section of the textbook, just because they are nice accurate graphs. If you've not got squared paper, it can be quite difficult to get them accurate. That concludes the lesson for today. See you next time.